let's unpack this. We're taking a deep dive into some really interesting research today. It's from case studies in chemical and environmental engineering, and it's all about improving materials for bone repair.
Right. Specifically looking at hydroxyapatite, HA.
HA, yeah, which is already quite similar to our bones, isn't it?
Exactly. That's the appeal. It's biocompatible because, well, it's basically a mineral component already found in bone and teeth.
Okay, so what's the problem they're trying to solve here?
Well, the main challenge with using HA to make scaffolds, like frameworks for new bone to grow on, is getting the properties just right.
Properties like strength.
Strength, yes, absolutely.
Yeah.
But also porosity. You need those tiny interconnected holes for, cells to move in, for tissues to grow, blood vessels to form.
Ah, right. So it needs to be strong enough, but also porous enough. That sounds like a tricky balance.
It really is. Make it denser, it gets stronger, but less porous. Make it more porous, it helps tissue ingrowth, but it might be too weak.
So this study looked at how the manufacturing process affects this balance.
Precisely. They focused on one specific step called sintering.
Sintering, that's like high-temperature baking, right? To fuse powder together.
Yeah, basically. You heat the material, but not quite to melting to bond the particles. And they look specifically at the dwell time.
Dwell time, meaning how long you keep it at that top temperature.
Exactly. In this case, the peak temperature was 900 degrees Celsius. They tested holding it there for 2 hours, 4 hours, and 6 hours.
And the HA powder itself, where did that come from?
They actually derived it from a natural source, animal bones, and they used a low-compaction method to form the initial shapes before sintering.
Okay, so natural source, low compaction, 900 degrees C, and varying the dwell time. What did they find? Let's say maybe hardness first. Seems crucial for bone.
It is, and the results were quite clear. A longer dwell time meant higher hardness.
So the 6-hour samples were the hardest?
Yes, significantly so. They measured what's called micro-hardness resistance to a very localized pressure, and the 6-hour samples came out on top.
How hard are we talking? Like, compared to actual human bone?
That's the really interesting part. The values they got for the 6-hour samples, around 0.5 gigapascals, GPa, that's actually comparable to the hardness of older human cortical bone.
Cortical bone, the hard outer layer.
Yep, the dense part. So hitting that kind of hardness is, well, pretty promising, especially maybe for areas that don't bear huge loads.
Okay, that's impressive for hardness. But what about the trade-off? Did they lose all the porosity by sintering for longer?
You'd often expect that, wouldn't you? More sintering usually means less pore space.
Right.
But here's the twist. The 6-hour dwell time didn't just give the highest hardness. It also gave the highest porosity among the tested times.
Really? Both went up?
It seems so for this specific material and process. They reported porosity values upwards of 50% for the 6-hour samples using some methods.
Wow. So you get the hardness and the open structure needed for cells.
It looks that way. A more open, interconnected pore structure, which is exactly what you want for tissue integration, getting nutrients in, waste out. It's kind of a win-win in this case.
Okay, that's fascinating. Did they check how stable these things were, like in the body?
They did. They put the samples into simulated body fluid SBF, which mimics the ionic environment inside us. Well, all samples gained a bit of weight, as expected when they soak up fluid. But the 6-hour samples also showed higher crystallinity, which suggests they might be, more stable structurally over the long term compared to the ones sintered for less time. Another positive sign.
So experiments look promising for the 6-hour mark, but the paper also mentioned computational work, DFT.
Ah, yes. Density functional theory. That's a computational chemistry method. They used it to model the HA crystal itself, like at the atomic level.
Why do that?
It helps understand the intrinsic properties, like what's the theoretical maximum hardness of a perfect HA crystal? What's its ideal structure? It gives you a sort of fundamental baseline.
Okay, a theoretical ideal. But I think the paper noted the DFT prediction for hardness was way higher than what they actually measured in the lab samples.
It was.
Yeah.
That's a really important point. The DFT model looks at a perfect infinite crystal, often at absolute zero temperature. Real-world samples aren't like that.
How so?
Well, the lab samples are made from powder. They have grain boundaries where crystals meet. They have tiny defects. And, crucially, they have all that porosity we just talked about.
Yeah.
All those things reduce the actual measurable strength and hardness compared to the perfect theoretical model.
So the model gives the potential, the experiment shows the reality of the process material.
Exactly. The simulation is powerful for understanding the fundamentals, but bridging that gap to real complex materials with pores and imperfections, That's still a challenge.
Okay, so pulling this all together, what's the main takeaway from this deep dive?
I think the key finding is that, at least for HA made this way from natural bone, low compaction sintering at 900 degrees C for a 6-hour dwell time seems to hit a real sweet spot.
A sweet spot.
You get significantly improved hardness, getting into the range of actual cortical bone, plus you maintain or even enhance that beneficial high porosity, and good signs for stability too.
And the computational side.
It highlights how these tools like DFT are advancing our basic understanding, even if predicting the exact behavior of these complex, porous, real-world biomaterials is still, tricky.
Right.
It definitely gives valuable insights for tuning these materials, though.
Right. So thinking about this, it really does make you wonder. We know we need implants that are strong and porous for the body to truly accept and integrate with them.
Mm-hmm. The holy grail, really.
So given this research optimizing processing for natural materials, how much further can we actually push this? How much better can we get at refining these natural material processes and maybe improving the predictive power of our models to truly custom engineer the perfect bone scaffold for each specific need?